Welcome to today's session. We'll be tackling an exciting problem from the domain of string manipulation and array traversal, problem number 245, shortest word distance 3. In this problem, we'll explore various approaches to finding the shortest distance between two words in a dictionary under specific conditions. Let's dive in. In this problem, we are tasked with finding the shortest distance between two words in an array of strings called wordsdict. These two words, word 1 and word 2, can either be the same or different. This makes it an extension of a simpler problem where the two words are always different. The key here is to determine the smallest number of indices between the occurrences of these two words in the list. The input includes wordsdict, which is an array of strings, and the two words, word 1 and word 2. The output is an integer that represents the shortest distance between these two words within the array. The problem also guarantees that both word 1 and word 2 will always be present in wordsdict, so we don't need to handle cases where either word is missing. Let's look at the first example to understand the problem better. Here, wordsdict is an array containing the strings practice, makes, perfect, coding, makes. The word 1 is makes and word 2 is coding. To solve this, we locate the first occurrence of makes, which is at index 1, and the first occurrence of coding, which is at index 3. The distance between these two indices is calculated as the absolute difference, 3, 1, which equals 2. Since this is the smallest distance between these two words in the list, the output is 2. In the second example, the input wordsdict is the same, but here both word 1 and word 2 are the same word, makes. The goal now is to find the shortest distance between any two occurrences of the word makes. The first occurrence is at index 1, and the next occurrence is at index 4. The distance between these indices is 4, 1, which equals 3. Since this is the shortest distance between any two instances of makes in the list, the output is 3. In the third example, wordsdict is A, C, A, B, C, A, and the words word 1 and word 2 are A and C, respectively. The first occurrence of word 1, A, is at index 2, and the first occurrence of word 2, C, is at index 3. The distance between these indices is a 3, 2, which equals 1. This is the shortest distance between A and C in this list, so the output is 1. The constraints of the problem also emphasize that the solution should handle large arrays efficiently, and we must account for edge cases, such as when the two words are the same or appear multiple times in the list. To solve this problem, we first consider the brute force approach. The intuition here is straightforward: iterate over all possible pairs of indices in the array to find where word 1 and word 2 occur. For each pair, you calculate the absolute difference between their indices and keep track of the smallest distance found. This method involves traversing the array to locate all occurrences of word 1 and word 2. Then, for every index of word 1, you compare it with every index of word 2. If word 1 and word 2 are the same word, an additional step ensures that we only consider distinct indices. Finally, the smallest distance is returned. While this approach is simple to understand and implement, its inefficiency becomes apparent in terms of time complexity, which is O, n superscript 2, due to the nested comparisons. On the other hand, the space complexity is O, 1, as no additional data structures are required. The inefficiency of the brute force approach stems from the nested comparisons, which make it unsuitable for large arrays. With this in mind, we shift to a more optimized approach. The key insight here is to use two pointers, index 1 and index 2, to track the most recent positions of word 1 and word 2 as we traverse the array. This eliminates the need for nested loops. The process begins by initializing index 1 and index 2 to -1 and setting min_distance to infinity. Then, as we iterate through the array, we update index 1 whenever we encounter word 1 and index 2 whenever we encounter word 2. If both indices are valid, we calculate the distance between them and update the minimum distance if necessary. For the special case where word 1 and word 2 are the same, we ensure that the same index is not reused, maintaining the integrity of the solution. At the end of the traversal, the smallest distance is returned. The optimized approach offers significant improvements over the brute force method in terms of complexity. By traversing the array just once, we achieve a time complexity of O, n. Additionally, the space complexity remains O, 1, as no extra data structures are utilized. The key realization here is that we don't need to pre-compute and store all the indices of word 1 and word 2. Instead, dynamically updating their most recent positions during the traversal is sufficient. This not only reduces the overhead but also streamlines the implementation. However, special care is required for cases where word 1 and word 2 are the same, as we must avoid using the same index twice. This minor adjustment ensures that the solution is both correct and efficient. The optimized approach is chosen because it strikes an ideal balance between simplicity and efficiency. Unlike the brute force method, it avoids unnecessary pairwise comparisons by leveraging the sequential nature of the array. This reduces the time complexity from O(n) superscript 2 to O(n), making it far more scalable for larger datasets. While the optimized approach introduces a slightly higher implementation complexity, particularly in handling the case where word 1 equals word 2, this trade-off is minimal when compared to the substantial performance gains. The overall strategy ensures that the solution remains efficient and easy to debug, making it the preferred choice. To summarize the comparison, the brute force approach, with its O(n) superscript 2 time complexity, is simple to implement but becomes impractical for large inputs due to its inefficiency. Conversely, the optimized approach, which uses 2 pointers to track the most recent positions of word 1 and word 2, achieves a linear time complexity of O(n), while maintaining O(1) space usage. This makes it not only efficient but also scalable. The optimized method does require additional checks, particularly for edge cases, such as when word 1 and word 2 are the same, but these are minor complexities in exchange for the significant performance benefits. Ultimately, the optimized approach stands out as the best solution, providing a robust and efficient way to solve the problem. In this problem, we are tasked with finding the smallest distance between two specific words, word 1 and word 2, within a given list of strings, wordsdict. The distance is measured in terms of the indices of their occurrences. If one or both of the words are missing from the list, the algorithm should return a special value, such as -1, to indicate this. The brute force approach to solve this involves first identifying all the indices where word 1 and word 2 appear in the list. To do this, we iterate through the entire list, storing the indices of word 1 in one list, say positions 1, and the indices of word 2 in another list, positions 2. After collecting these indices, we compare every possible pair of indices from positions 1 and positions 2, calculating the absolute difference between them. By keeping track of the smallest difference found, we can determine the shortest distance. However, while this method is straightforward, its inefficiency for large inputs makes it less practical for real-world scenarios, as it involves nested loops to compare all possible pairs. The brute force approach continues by iterating over all pairs of indices from positions 1 and positions 2. For each pair, we calculate the absolute difference and keep track of the smallest difference using a variable, min distance. This ensures we find the shortest distance between any occurrence of word 1 and word 2. Finally, after all comparisons, we return the minimum distance found. If either positions 1 or positions 2 is empty, meaning one or both words are missing, the algorithm returns -1 to indicate this. To address the inefficiency of the brute force approach, we can adopt an optimized solution that avoids comparing all pairs. This optimized method uses a single pass traversal to achieve O(n) time complexity. First, we initialize two variables, lastPos1 and lastPos2, to -1. These will store the most recent indices of word 1 and word 2, respectively. Additionally, we set min distance to a very large value, such as infinity, to track the smallest distance encountered during the traversal. By using these variables, we can eliminate the need for nested loops and significantly improve performance. Now, during the traversal of the list, whenever we find an occurrence of word 1, we update lastPos1 to its current index. Similarly, when we encounter word 2, we update lastPos2. After updating either variable, we check if both lastPos1 and lastPos2 have been set to valid indices, meaning neither is still -1. If both are valid, we calculate the absolute difference between the two indices and compare it with the current value of min distance. If the new difference is smaller, we update min distance accordingly. This greedy approach ensures that we keep track of the shortest distance encountered so far without having to revisit previous indices. Once the traversal is complete, we return the value of min distance. However, if min distance remains at its initial value of infinity, it means one or both of the words were never found in the list, and we return -1. This method is more efficient because it avoids the quadratic time complexity of comparing all pairs, instead leveraging the fact that we only need the most recent indices of the two words to update the minimum distance in a single pass. To implement this optimized approach, we use simple data structures to reduce both time and space complexity. Instead of maintaining separate lists for the indices of word 1 and word 2, we use two integer variables, lastPos1 and lastPos2, to store the most recent indices of the words. This change reduces the space complexity from O(n) to O(1). Additionally, we use a single variable, min_distance, to track the shortest distance found during the traversal, further simplifying the algorithm. The pseudocode for this approach begins by initializing lastPos1, lastPos2, and min_distance. We then iterate through the list, updating lastPos1 or lastPos2 whenever we encounter word 1 or word 2, respectively. Each time both indices are valid, we calculate their absolute difference and update min_distance if the new difference is smaller. At the end of the loop, we return min_distance if it has been updated, or -1 if one of the words was not found. This streamlined structure makes the algorithm both efficient and easy to implement. The optimized algorithm has a time complexity of O(n), because it only requires a single traversal of the list, where n is the size of words ticked. The space complexity is O(1), as it uses only a constant amount of extra space to store the indices in minimum distance. This makes the solution both time and space efficient. To ensure the algorithm handles edge cases correctly, we consider several scenarios. First, if either word 1 or word 2 is missing from the list, the function should return -1, as there is no valid distance to calculate. For example, if words ticked contains only A, B, C and word 1 is X, the output would be -1. Another edge case arises when word 1 and word 2 are the same. In such cases, the algorithm should clarify whether self-distance is allowed, as this depends on the problem's definition. Lastly, when word 1 and word 2 are adjacent in the list, the distance is guaranteed to be 1, which is the smallest possible value. These examples highlight the robustness of the algorithm in handling various input scenarios. This solution efficiently computes the shortest distance between the given words in the list. The function shortest word distance takes three arguments: words ticked, a list of words, word 1, and word 2. The algorithm uses a single pass through the list, maintaining a prev_index to track the last occurrence of either word 1 or word 2. As we iterate through words ticked, if the current word matches either word 1 or word 2, we check if the conditions to compute the distance are met. If word 1 and word 2 are the same, we ensure we don't compute the distance between the same index. Otherwise, we calculate the distance and update min_distance if the new distance is smaller. Finally, prev_index is updated to the current index. This approach ensures an O(n) time complexity since we traverse the list only once, and space complexity is constant, O(1), as no additional data structures are used. This is the Java implementation of LeetCode problem number 245, shortest word distance 3. It mirrors the Python logic exactly, with key differences being the use of Java-specific constructs such as arrays, type declarations, and the equals method for string comparison. The solution maintains a variable to track the previous index where a word match occurred and calculates the shortest distance dynamically. The code is concise and adheres to Java conventions. To solve the problem of finding the shortest distance between two words in a list, we start with the first example where the words are different. The input consists of a list of words, words ticked, and the target words word 1 is coding and word 2 is practice. Initially, we set up two variables, min_distance as infinity to keep track of the smallest distance found, and prev_index as -1 to store the most recent index of a matching word. As we iterate through the list, on the first step, the word at index 0 is practice, which matches word 2. Since prev_index is still -1, we don't calculate a distance yet, but we update prev_index to 0. On the next step, at index 1, the word is makes, which matches neither word 1 nor word 2, so we simply move on. At index 2, the word is perfect, which again doesn't match either of the target words, so we continue. Then, at index 3, the word is coding, which matches word 1. Now that prev_index is not -1, we calculate the distance as the current index minus prev_index, or 3 minus 0, which equals 3. We update min_distance to 3 and set prev_index to 3. Finally, at index 4, the word is makes, which doesn't match either target word, so no changes are made. The shortest distance between coding and practice is therefore 3. Moving to the second example, we now have word 1 and word 2 both set to a. In this example, where the target words are the same, we initialize min_distance to infinity and prev_index to -1, just as before. At index 0, the word is a, which matches both word 1 and word 2. Since prev_index is still -1, no distance is calculated, but we update prev_index to 0. At index 1, the word is b, which doesn't match the target words, so we move forward. At index 2, the word is c, which also doesn't match. Then, at index 3, the word is a, which matches the targets again. Now, with prev_index at 0, we calculate the distance as 3 minus 0, which equals 3. We update min_distance to 3 and set prev_index to 3. At index 4, the word is b, which doesn't match the target words, so we continue. At index 5, the word is a, which matches both word 1 and word 2 again. This time, with prev_index at 3, we calculate the distance as 5 minus 3, which equals 2. We update min_distance to 2 and prev_index to 5. The shortest distance between occurrences of a is therefore 2. In the third example, the list contains consecutive matches for the target word x. Here, both word 1 and word 2 are again the same, set to x. We initialize min_distance to infinity and prev_index to -1. At index 0, the word is x, which matches the targets. Since prev_index is -1, we don't calculate a distance yet, but we set prev_index to 0. At index 1, the word is y, which doesn't match the targets, so we move forward. At index 2, the word is z, which also doesn't match. Then, at index 3, the word is x, which matches the targets again. With prev_index at 0, we calculate the distance as 3 minus 0, which equals 3. We update min_distance to 3 and set prev_index to 3. At index 4, the word is x, which matches the targets once more. This time, with prev_index at 3, we calculate the distance as 4 minus 3, which equals 1. We update min_distance to 1 and prev_index to 4. The shortest distance between occurrences of x is therefore 1. This approach ensures we efficiently find the minimum distance between two words, even when they are the same, by iterating through the list just once and updating the required variables as we go. The time complexity of the solution is determined by the fact that we iterate through the words_dict list just once. This means that for an input list of size n, the loop runs n times. Within each iteration, we perform a few constant time operations. First, we check if the current word matches either word 1 or word 2, a comparison that takes 1 time. Then, if one of the words matches, we enter a conditional block where we calculate the potential new minimum distance and update min_distance if needed. These calculations, such as subtraction and the min function, also take 1 time. Finally, we update the prev_index variable, which is a simple assignment operation and similarly takes 1. Since these operations are constant time and repeated for all n elements in the list, the total time complexity is n. Now, when analyzing the best, average, and worst cases, the time complexity remains consistent. Even in the best case, where word 1 and word 2 appear early in the list, the algorithm still processes all elements to ensure no closer pair exists. This makes the time complexity n. In the worst case, where word 1 and word 2 are at the very end of the list or appear multiple times, the algorithm must still iterate through every word and perform all necessary comparisons and updates. Thus, the time complexity does not change and is still n. For space complexity, the algorithm uses only a constant amount of extra space. Variables like min_distance, prev_index, and the loop index I are scalars, meaning they occupy fixed space regardless of input size. Importantly, the input list words_dict is not duplicated or modified, so it doesn't contribute to extra space usage. This gives the algorithm a space complexity of 1. To better understand the efficiency of this approach, let's compare it to the naive solution. A brute force method would involve iterating through all possible pairs of indices in the list to calculate distances, which requires 2 nested loops. For a list of size n, this results in n squared time complexity. However, the brute force method, like the optimized approach, still uses O1 space since no additional data structures are needed. The optimized solution, on the other hand, eliminates the need for nested loops by using a single pass approach and a pointer, prev_index, to track the last occurrence of word 1 or word 2. This reduces the time complexity to n, making it significantly more efficient for larger inputs, while maintaining the same O1 space complexity. Mathematically, the time complexity is confirmed as n, because the algorithm performs exactly n iterations, with each iteration involving constant time operations. This linear relationship holds true regardless of how word 1 and word 2 are positioned in the list, reinforcing the efficiency of the solution. When working on this problem, there are a few common mistakes to watch out for. First, not accounting for the order of word 1 and word 2 indices can cause issues, especially if the problem specifies that the order of their appearance matters. Ignoring this can lead to incorrect calculations of the minimum distance. Another pitfall is using nested loops unnecessarily. While a brute force solution that iterates over all pairs of indices for word 1 and word 2 might seem straightforward, it results in a time complexity of n squared, which becomes highly inefficient for large input sizes. Lastly, failing to handle edge cases is a frequent oversight. For example, the words dict array might not contain one or both target words, or word 1 and word 2 might be the same word. These scenarios, if missed, can lead to runtime errors or unexpected outputs, which can be a red flag during interviews. Another mistake to avoid is not updating indices optimally during traversal. In a single pass solution, if you forget to update the index of word 1 or word 2 when encountering a match, you risk comparing outdated indices, which can result in missing the true minimum distance. Additionally, overcomplicating the solution is a common issue. For instance, introducing unnecessary data structures like hash maps, when a simple two-pointer approach would suffice, leads to increased time and space complexity. Successful interview performance often hinges on a few key insights. Recognize that this problem is a variation of the two-pointer or sliding window technique, which is a popular pattern in array and string problems. Interviewers tend to focus on your ability to optimize from a naive n squared approach to an n solution, so outlining your thought process clearly is important. Always clarify edge cases with the interviewer, such as scenarios where word 1 equals word 2 or where the input list is empty. Highlighting these details demonstrates thoroughness. Finally, be ready to discuss space versus time trade-offs, especially if you choose to use additional data structures for your solution. It's also helpful to explore related problems to deepen your understanding. For instance, LeetCode 243, 244, and 245 all focus on variations of the shortest word distance problem, while LeetCode 532 introduces a different challenge involving k-diff pairs in an array. In terms of alternative approaches, the two-pointer method offers an elegant solution with n time complexity. By traversing the array once, you can keep track of the last seen indices of word 1 and word 2 and dynamically calculate the minimum distance. This approach is both simple and efficient, but it does have a limitation when word 1 and word 2 are the same, as additional logic is required to handle this special case. Another approach involves pre-processing the data with hash maps. This method requires n time for pre-processing, as you store all indices of each word in a hash map. Once the indices are pre-computed, you can calculate the minimum distance using two sorted lists of indices, making queries more efficient with a time complexity of m plus k, where m and k are the sizes of the respective lists. However, this approach increases space complexity to n, which is a trade-off to consider. Finally, binary search on sorted indices is another option. Here, you sort the indices of word 1 and word 2, then use binary search to find the closest pair. While this method is efficient for sparse arrays, with a time complexity of n log n, the overhead of sorting can make it slower for dense arrays. Each of these approaches has its strengths and trade-offs, and understanding them will help you choose the right solution based on the specific problem constraints. That wraps up our discussion for today. We reviewed the shortest word distance 3 problem, its efficient solutions, and key takeaways. I hope this session gave you valuable insights and strategies to tackle similar problems. Thanks for watching, and I'll see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!